Yes, is my screen visible to everybody? Yes, students, is my screen
Yes, sir.
visible?
Yes,
Okay,
sir.
fine. So we will continue now. So in the previous class, we have taken a numerical, right? So we have taken this numerical, and we have seen how the discretization is going to affect your results. Okay. So today we are going to continue from this point. So generally, if you remember, we have a force term, isn't it? So this force term, okay, so this force term usually it is consisting of three parts. Okay, one is the force due to the point loads, okay, plus the force, okay, due to the surface load, plus the force due to the volume load. Okay, we have one more term over here, that is the force due to the initial strain, and this initial strain can be due to the change of the temperature, right? So let us quickly see the different types of the force. Okay, how the nodal forces are calculated with the help of this finite element method. Okay, so let us quickly see the first part, that is the this load, that is the volume load. Okay, give me a moment. Yes. So we have already seen, if it is a point load. Okay, so if you have a problem which is something like this, okay, and if there is a load which is acting at this point, so let us say this is node number 1 and this is node number 2. So what we generally do, if it is acting in the direction of the axis, so at node number 1 there is no force, so we are considering this as 0, and at node number 2 we are considering this as p. So whatever values are there, that you have to substitute in the force matrix, that is the local force matrix, as the direct values. Okay, but when it comes to the surface load, okay, so this is your surface load. So in that particular case, for surface load, you have to go for some small integration, that is integration over the surface. Okay, we have this n transpose. So n is nothing but your shape function into, let us say, I'm using a symbol called as t. Okay, so t is nothing but your surface load, and this has to be integrated over the surface. Okay, similarly, we have a volume load also. Okay, so in case of volume load, this has to be integrated over the volume, and then it will be multiplied with the shape function transpose, multiplied by, let us say, this side we have v and this is dv. Okay, so here t is nothing but your surface force. Okay, and here your b is nothing but volume force. Okay, so just for sake of example, we will see how the loads are calculated over here, right? So let us take a simple example of a simple bar. So this is, let us say, one bar. Okay, so I am intentionally drawing this bar as a vertical bar. Let us say this is node number 1 and this is, let us say, node number 2. Okay, so for example, the density of the material of this particular bar is given to you, and let us say it is given to you in form of a rho. So this is nothing but your density. Okay, and if you remember, while designing or for while deriving the expression of the stiffness equation, we have used this as length, and we have used area as a constant. Okay, so this will be area. A is nothing but your area, and this L is nothing but your length. Okay, so now ideally what has to be done? So if you want to calculate the total weight of this bar, so your total weight W can be calculated as the area into length. So this is nothing but the volume, okay, multiplied by the density. So this is going to give you a total weight, and ideally what has to be done, this total weight will be divided into equally two parts. That is, one load will be applied at node number 1 and the remaining load will be applied at node number 2. The same thing can be done over here. So here, if you want to calculate the force at volume force over here, so here this will be integration over the volume. This will be N transpose into B into dV, right? So this can be rewritten in form of, let us say, N transpose. What is your N? N is nothing but your shape functions. Okay, so if N is there, then we have N1 and N2. I am writing it in a vertical form because it is transpose. And B is nothing but the volume force. So volume force can be written in form of a this symbol, okay, rho. And dv can be written as simple area into dx. Okay, so dx, if you integrate, it is going to become L, and these limits are going to change to L. So here, in short, what we have rho, we have A, okay, which will come out, and we have integration of this N1, N2, okay, this is L, and this is over dx. Okay, so now if you go for the first part, okay, so I am highlighting the first part over here. So this is my first part. Okay, so this is my first part. So if I take the first element of the force matrix, so let us call this as F1. Okay, so F1 now can be rewritten as rho into A. This is integration over the length into N1 into dx. Okay, so this is rho into A, integration over the length, and if you remember, the shape function value of node 1 is 1 minus x upon L over dx, isn't it? So if you go for the integration of this, so what you are going to get? Can somebody tell me what you are going to get? 1 minus x upon L, integration over the length. Yes, please. Bolo. Yes, students, please respond. Yes, students, please respond. What will be the integration? Yes, students, please respond. What will be the integration? Krunal, your voice is not, you are not audible. Yes, anybody else?
L by 2.
L by 2. Okay, so because this finally it is going to become L by 2. Okay, so finally this F1 value is nothing but rho into L into A divided by 2. So basically this is exactly the half of this A L into rho. Okay, तो यही चीज जो है तुम्हारी यहाँ पे आएगी. Only thing is it is divided by 2. Okay, similarly if you go for F2, so F2 is nothing but your this term. Okay, that is the second term over here. Okay, so this can be rewritten as this is rho into A into L by integration over the length of N2 into dx. So I can take out rho A, this is integration over the length, and your N2 is nothing but x by L over dx. And if you go for the integration of this, so then also you are going to get AE upon L divided by 2. Okay, so in this way you can get the value of the force at the second node. So basically whatever total load is there, it is equally divided among the two nodes. Okay, so finally your FV, which is the volume load, so it can be simply written as rho A L divided by 2, and here you have 1, here you have 1. Okay, so this is how the surface the volume load can be generated. Okay, similarly on the similar lines you can also go for the calculation of the surface load. Okay, so only thing is some slight changes will be there. Okay, so here you have only the T. So in place of rho we have now T. The area will not come into picture, so this will be only L upon 2, and this will be 1 and 1. Okay, so it's very rare case that you will get a surface force in the bar element. Okay, so have you understood this? Yes, is there any questions? Yes, students, are there any questions? Please let me know. Is it okay?
Yes,
Yes,
sir.
yes. Yes, sir.
All right. Now coming to the initial strain part. Okay, so like here you see we have three terms, that is force due to the point load, then due to the surface load, then due to the volume load, and then due to the initial strain. This is mainly due to the temperature. Okay, so let us quickly calculate how this force due to the initial strain can be calculated. Okay, so I am going for initial strain. Generally it is denoted by strain 0. Okay, so usually it is calculated by a expression, that is integration over the volume, then we have V transpose into D, okay, into the initial strain. Whatever is the initial strain value, that has to be done, and it has to be integrated over the volume. Okay, so now in case of 1D problem, you remember this D value is nothing but your E value. Okay, and this dV can be written as A into dx, and in that particular case your integration limits are going to change to integration over the length. So this value now can be written as, this is integration over the length, so your B transpose. Okay, so B transpose is nothing but minus 1 upon L and 1 upon L. So B transpose is nothing but the transpose of strain displacement matrix. Okay, this we have already seen in the derivation. So your D value is nothing but your E. Okay, and your initial strain, so your initial strain is nothing but you have the temperature effect, right? So temperature effect, this can be calculated by just going for alpha into T. Okay, and here the same thing will come, that is A into dx. So if you go for this calculation of initial strain, so what you are going to get is if you take out all the integration constants outside, so in that particular case you are left with only alpha T A E, and here we have now two terms, one will be the -1 and second will be the +1. So this is nothing but the forces which are there due to the temperature for a bar element. Okay, have you understood this, everybody? Are there any questions, please?
Sir,
Yes, students. Sorry,
second step, alpha T.
Alpha T.
That should that you have written alpha L.
Oh, sorry, my mistake. Just a moment, I will start with the numerical. Let me take out a numerical first. So this is alpha T. Okay, so let us take a small numerical based on the temperature effect. So let me put a let me end this section over here. Okay, okay, so what I'm going to do is I'm going to create a simple I don't know whether the shape is there or not. Anyway, so I'll draw it. Okay, so I have a numerical. I think this was asked in some of the examinations, so I want everybody to pay attention to this one. So we have a shape which is something like this. Okay, and it is like this only, and at the center. Okay, so let me draw a line over here. Okay, so at the center, somewhere over here, okay, I have a point which is like this. Okay, oh, the line is gone. Okay, so this is at the center. So at this point we have a load which is acting, its magnitude is 10 kilonewton. Okay, and at the same time at this point, okay, the load is also acting and its value is 5 kilonewton. Okay, so this is what is given to you, right? As far as the area is concerned, okay, so here the diameter is given to you. So the diameter of this is a kind of a bar. Okay, and its diameter at the end, it is given to you as 16 millimeters, and here the diameter is given to you as 20 millimeters, and the distances, okay, so here the distances are also mentioned over here. Okay, so this it is equidistance. So here it is 1 meter, and here also it is 1 meter. Okay, so naturally, if this is 16 and this is 20, so at this level the diameter will be something like 18 millimeters. Okay, at the same time, what is happening over here is we have been given a temperature effect. So the alpha, that is coefficient of thermal expansion, is given to you as 10 into 10 to the power minus 6. This will be per degree centigrade, and the delta T, that is the rise in temperature, is given to you as say 30°C. Okay, so now we have to analyze this particular problem, and we have to find out what are the deformations. Okay, so let us try to solve this. Okay, so before solving, we have to discretize this particular problem. This is the first step of the finite element method. So what I'm going to do is I'm going to discretize this using only two elements. Okay, so let us call this is node 1, this is node 2, and this is node 3. So let me put a numbers over here: node 1, node 2, node 3. Okay, then I'm going to give this as element number 1. Okay, and this is element number 2. Okay, so now here you see what is happening over here is the area at three different node, it is exactly different. Okay, they are not same, the area is varying. So what we have to do is we have to follow the process which we have done in the previous problem. We have to take the average area. Okay, so can somebody tell me how much is the area? Okay, yes, please, somebody tell me how much is the area. So at this level, okay, at this level how much is area, at this level how much this is area, and at this level how much is the area. So this is pi by 4, 16 square. How much is this? Yes, somebody please tell me. Batao bhai. See, you have to do the calculations. I am not going to do the calculations.
Sir, 201.06.
201.06. 06. Okay, and how much is the area at this middle? That is pi by 4 into 18 square.
254.47.
254.47. Okay, and at this fixed end,
314.16.
314.16. Okay, so these are the areas of the at three different locations. So what we can do, if you remember what we have done in the previous case, we have taken the average of this. Okay, and this average area we have given this average area to element number 1. Okay, so can somebody tell me how much is the average area of average value of this two? That is 314 and 254.
$264.31.
Sorry,
264.31.
please somebody cross check if it is correct or not.
Sir, 284.315.
Yes, exactly. It should be 280.
1.315.
281 or 284?
284.315.
31. Okay, so this is the average area of the element 1, you can say. Okay, so now similarly you can calculate what is the average area of element 2. Okay, how much is the area average? That is 254 plus 201 divided by 2. How much is that?
227.765.
227.76. Okay, so basically what we are doing is now that we have converted the given problem into like this. Okay, let me draw another figure over here. So what, in place of that tapered bar, we are now assuming our problem is something like this. Okay, okay, so let me slightly move this over here. Okay, so now this is our problem now, right? Such that the average area of this particular element is, here it is 284.31, and here average area is nothing but 227.76. Okay, so this is what we have done now, right? So modulus of elasticity, I think I have missed this. Modulus of elasticity is also given to you, that is 200 into 10 to the power 6. This is kilo newtons per meter square. So this is given to you. Okay, so now we have successfully done the discretization of the problem. And remember, the length over here of the element 1 is 1 meter, and the length of the second element is also 1 meter, because it is also mentioned in the problem, it is 1 meter each. Okay, so the discretization is now completely done. So now all we have to do is generate the local stiffness matrix. Okay, so your K1. Okay, generally the K expression, that is K expression, is A E upon L. This is 1 minus 1 minus 1 and 1. Okay, so this is a generalized expression. So now if you want to go for the elemental stiffness matrix for first element, so this will be A1, E is constant, L1. Okay, and then multiplied by 1 minus 1 minus 1 and 1. Okay, so now in this particular case, the value of A1, so A1, that is the first element value, so the cross section area is 284.3. Okay, so this is in millimeter square, isn't it? So what we have to do is just multiply it with 10 to the power minus 6, so that it becomes meter to the power 2. Okay, and then your value of modulus of elasticity is 200, okay, into 10 to the power 6. This is in kilonewtons and meter square, divided by the length of the first element is 1 meter. Okay, so can someone tell me how much is the constant which is outside this brackets? कितना आ रहा है?
56862.
56862.
8 56862.
56862.
Yes, sir.
Okay, so this is 1 minus 1 minus 1 and 1. Okay, so similarly you can generate the elemental stiffness matrix for second element. So this will be A2 into E divided by L2. Now here 1 minus 1 minus 1 and 1. So here what you are going to get is the A2 area. So the second element has got area 227.76. This is millimeter to the millimeter square. So if you multiply it with 10 to the power minus 6, so this will be meter square. The modulus of elasticity is still same. Okay, and the length of the element is 1 meter. Okay, so this is 1 minus 1 minus 1 and 1. Yes, can somebody tell me the value, please? Constant value?
45552.
45552. Correct?
Yes, sir.
1 minus 1 minus 1 and 1. Okay, so in this way you can generate now K1 and K2, right? Now let us go for the assembly. For assembly we have to find out, let us say this is your K1. K1 has got connectivity from node number 1 to node number 2. Okay, whereas the K2 has got connectivity node number 2 to node number 3. Okay, so the same thing can be done in form of assembly over here. So your K global. Okay, so your K global will be something like this. Okay, let me put a straight line over here. Straight line over here. Okay, and bracket over here. Okay, so I am going to substitute this values now. So this is the first value. Okay, so this first value can be written over here, that is, this is 56862, because this is multiplied with 1. Okay, then the second value is this value. Okay, so this value and this value both are same. Okay, so this has to be multiplied with minus sign. So this is minus 56862. This will be also minus 56862. Okay, now the remaining part is this part. Okay, which is this one over here. It is its location is 2 2. Okay, remember this is your node number 1, node number 2, node number 3. This is node 1, node 2 and node 3. So this orange color value, this will be written over here, that is 56862. Then comes the second element. Okay, so the second element, this value, that is this value. Okay, so it has to be located in second row and second column. So this will be added over here. So this is 45552, and the rest of the values will be minus 45552. This will be minus 45552, and this will be 45552. These values, they will be 0. Okay, I hope you have understood this. Okay, so can you just tell me the summation of these two at the center, 2 2? How much is the summation? Yes, somebody please tell me the summation values.
102414.
Okay, let me write down. This is
2414.
2414. Okay, so this is nothing but your final global stiffness matrix for the entire problem. Now coming to the force matrix. Okay, so just now we have seen your force matrix. Okay, so force global, it will be consisting of the force which is nodal force, okay, plus the force due to the initial strain. Okay, so the force due to the nodal force over here. So here if you see the problem, at node 1 there is no load over here, but here there is a 10 kilonewton load, and here there is a 5 kilonewton load. So ideally what should happen over here, this should be 0, this should be 10, and this should be 5. It is pretty simple, right? Now the strain component, so here the strain is there due to the external or rather due to the temperature change. Okay, so just now we have seen this force due to the initial strain. Okay, this can be calculated using an expression something like alpha t, okay, into A into E, and this will be -1 and +1 over here. Okay, so now here you see there are two elements over here. Okay, this is element number 1 and element number 2. So we have to calculate this force element wise. So let me calculate this force element wise. So this is force in strain 1, okay, and this is force in strain second element. Okay, so you already have the value of alpha t, isn't it? So alpha t value is something like 10 into 10 to the power -6. This is per degree centigrade. Your temperature is basically the rise in temperature is given to you, that is 30, and this will be area of the first element. Okay, so area of the first element we have calculated this as 284.31. Okay, so let me write down over here, this is 284.31. this was millimeter to the power 4, so I'm just going for this was millimeter square, so I'm going for 10 to the power -6, so that it will become millimeter, it will be meter square. Okay, multiplied by the modulus of elasticity. So the modulus of elasticity is already given to you, its value is 200 into 10 to the power 6. Okay, so this will be -1 and this will be +1. Okay, so can somebody tell me what is the value, please? Yes, this will be in kilonewtons.
17.058.
Sorry,
17.058.
17.058.
Yes, sir.
Okay, and how about this one? Same. So one will be negative and one will be positive. Okay, now similarly for the second element, due to the rise in temperature, the values will be something like this. Only thing is the area is now changed. Okay, so area, if you refer, this is 227.76. okay, so this is 227.76. this will be 10 to the power -6, okay, meter to the power 4, meter square, sorry. This will be exactly same, -1 +1. Okay, yes, can somebody tell me what is the values?
13.665.
Sorry,
13.665.
this will be negative, right?
Yes.
And this will be plus 13.665. everything is in kilonewtons, right? So now remember the node or the element 1 has got connectivity from 1 to 2, whereas the second node has got connectivity second element has got connectivity from node 2 to node 3. So if you assemble this, okay, so you have to assemble the force matrix also. So your force due to the initial strain, so this can be something like this, okay. So we have a first element matrix that is minus 17.058, okay, and this will be 17.058. The third node is 0 over here, okay. This will be plus, this will be 0 over here, this will be minus 13.665, this will be plus 13.665, okay. So how much is the total then? Somebody please tell me. Yes, students, please tell me the values. बीच वाली वैल्यू बताओ. 17.058 minus 13.665.
3.39.
Sorry?
3.393.
3.396. Okay, this is positive, right? So this is your force due to the initial strain. Okay, so now if you refer to the global force matrix, we have to add this, isn't it? So we have to add this. So this is 0, 10 and 5. So your force global matrix, okay, so this is force global matrix, okay, this will be 0, 10 and 5, okay, plus you will be having something like minus 17.058, this is 3.396, this is 13.665.
So 3.393.
Okay. 393.
Yes,
okay,
sir.
Fine. Okay, fine. So this will be, I think, minus 17.058. okay, I think this is 13. okay, so this is 13.393, and how much will be this? 18.665. is it right? Yes, students, is it right?
Yes, sir.
Yes, sir.
Okay. So now we have the stiffness matrix as well as the vector. Okay. So our final expression of the stiffness matrix is K global. Okay. Into here you have delta global equals to, we have force global. Okay. So all we have to do is just write down these matrices one more time. So this is 56,862. Okay, so let me write down over here. So this is 56,862. This is minus 56,862. This is also minus 56,862. And I think in the center we have 102,414. So this is 102,414. Okay, and here we have 4,552. Okay, so this will be, I think, minus 4,552. This will be 0. This will be also 0. Minus 4,552, and this is 4,552. बराबर है ये? Okay. Multiplied by, you have U1, U2 and U3. These are the nodal displacements at node 1, node 2 and node 3, and this will be equals to, this is minus 17.058, this is 13.393, and this is 18.665. okay, so now out of which you know that U1 is 0, okay, because at the node 1 there is a fixed support. So what you can do is you can eliminate the first row, okay, and then you can eliminate the first column also. So at the end you will end up with only one simple matrix, which is consisting of 2 by 2 matrix. So this will be 1 0 2 4 1 4. This is minus 4 552. This is minus 4 552. This is 4 552. So this will be reduced stiffness matrix, you can say. This is U2, this is U3. This will be equals to something like 13.393, and this is 18.665. Okay, so now you have to just solve this. Okay, and tell me the value of u2, okay, and u3. Yes, somebody please tell me the value of u2 and u3. Solve this. Use your calculators. Yes, done students. Please let me know the values.
So U2 5.63 into 10 raised to power minus 4.
Sorry, u2 is
5.637 into 10 raised to power minus 4.
This will be in meters. Okay, and how about u3?
9.735 into 10 raised to power minus 4.
This will be also in meters. Okay, so in this way you can solve a problem and you can get the unknown displacement, and once the unknown displacements are known, you can get the value of forces or maybe stresses and strain that we have seen in the previous class. Okay, I hope this is clear to everybody. Yes, are there any questions please? Okay, so we will stop now. Tomorrow I think tomorrow there is a holiday, so we won't be having a lectures. Day after tomorrow we will continue as per your timetable. Okay, so now I want all of you to leave the meet. If there are any